Hello friends, welcome to this session. We are going to be talking about optimization in this session, okay? And we are going to speak about a specific type of optimization called gradient descent, okay? Gradient descent. And we are going to discuss various types of gradient descent. So let's get started. Okay. In our previous session, we talked briefly about what optimization was, okay, in the context of the binary linear classifier. And we said that optimization was essentially going to help us arrive at the best answer iteratively via incremental improvement in each iteration. So this was basically what we said we were going to do, okay. Now, what we are going to be doing in this session is we are going to first look at the general optimization problem, okay, using gradient descent. One type of an approach to solving the optimization problem is the gradient descent. So we will first look at general optimization using gradient descent, and we will subsequently look at using the idea behind optimization to solve the binary linear classification problem. Okay, so earlier I was going to sort of consolidate all of this into a single lecture, but that would end up being about an hour and a half. So I have decided to break it up into two sections. In the first section, we will look at general optimization using gradient descent, and subsequently we will look at the binary linear classification, which basically got us here in the first place. Okay, let's get started. How is an optimization problem structured? Okay, how is an optimization problem structured? Let's understand the big picture first before we dive into the details, as always. In an optimization problem, the first thing you do is define a metric that you want to either maximize or minimize. Okay, so a metric is basically a quantity that you want to optimize, which means depending upon your context, you either want to maximize something or minimize something. And the first step naturally is to define this metric that you want to optimize, right? Then what you do is, once you have defined this metric, then what you do is iteratively meaning step by step, you modify the model parameters so that the metric is improved in each step. So now let me explain this. Okay, so you understand what iteratively means. You're not going to arrive at the final answer in one step. You're going to go step by step, repeat same thing over and over again. That's what's meant by iteratively. You modify the model parameters. Okay, so what you would typically have is a model which has certain parameters that you can vary. In the context of the binary linear classifier, we would be varying the weights or the coefficients of the feature variables. Those would be the parameters in our control. And what you would do in each step is essentially modify the model parameters or the weights, so that the metric that you have defined is improved in each step, little by little. So iteratively, little by little, you keep improving the metric. That's how an optimization problem is usually structured. Okay. Clearly, if defining the metric is the first step, it would seem reasonable that the entire success of your approach would hinge on choosing a suitable metric, right? So choosing a suitable metric would be probably the most important thing in formulating a optimization problem. So let's talk about certain guidelines or certain rules of thumb, if you could call them, on how you would go about choosing a metric for your particular problem, right? So let's see what would be some of these guiding principles. First principle, clearly it should reflect what you want to accomplish. I mean, this would seem like a no-brainer, and it is a no-brainer. Clearly the metric that you choose should reflect what you want to accomplish. right? I mean, what you want to maximize or minimize. Now, although this seems simple, the reason I mention this here is there are multiple ways of selecting a metric, even for your problem. Okay, and you know, some metrics may work better than the others. But no matter which metric you decide to choose, it's always a good idea to invest some time in thinking about the metric that you want to select, okay? And make sure that it reflects exactly what you want to accomplish, okay? So choosing a metric, when you're choosing a metric, the first thing you should do is make sure that it reflects what you want to accomplish. Number two, at each iteration, we should know how to modify the model parameters to improve the metric. This is extremely important, right? I mean, I'd sort of done a rough hand calculation at towards the end of our previous lecture, where we were sort of randomly changing the model parameters or randomly changing the weights, and we knew that sort of changing these randomly was not going to get us anywhere, right? So your metric should be such that in each iteration, at every iteration, you should know exactly what to do, exactly how to modify your model parameters or weights so that the metric is improved in the next step. Because unless you are guaranteed of that improvement in your metric from step to step, you are not going to be making any progress at all. So your metric should be such that at each iteration, you should know how to modify the model parameters to improve the metric. Number three, we should know when to terminate. I mean, if this is going to be an iterative process, it cannot go on forever. And the metric that you choose should be such that when you stop iterating should be fairly obvious. Okay. So your iteration should essentially tell you when to stop, right? So this is point number three. Number four, again, a little bit tricky but important. Termination should be at a global optimum. What do I mean by this? Suppose you kept optimizing and suppose you kept improving the value of your metric and you decided to terminate at some point in time. How do you know that the answer that you have arrived at is the best possible answer, right? So if you want any sort of guarantees in terms of what any sort of guarantees that the answer where you have stopped is the best possible answer, the global optimum as I called it, the selection of the metric needs to be suitable, appropriate, right? So choosing certain metrics will lead to the global optimum via iterations. Choosing other metrics may not necessarily bring you to the best possible answer, okay? And finally, computationally efficient. Computationally efficient is like a practical consideration. The amount of computational resources or the time taken to do your calculations should not be excessive. I mean, it should be reasonable, it should be efficient, and it should help, the metric should be such that you arrive at your answers reasonably quickly. So these are certain guidelines that you need to keep in mind when choosing a metric, especially when you solve the practical problems that you will run into. Recap, right? Recap of some calculus from high school. It's going to be useful for us here. Let's see. Given a function of a variable, its derivative with respect to the variable calculated at a point tells you the rate of increase of the function at that point, right? I mean, we all know that, right? So you calculate the derivative of the function, evaluate it at a particular point, it tells you how quickly the function is increasing at that particular point. Let's take an example. Okay. I have taken a curve y equal to 6 minus 2 times 0.4x minus 3 the whole square and drawn it over here. It's a parabola, right? And its derivative is, if you evaluate it using the chain rule, it is minus 1.6 times 0.4x minus 3. Okay. If I evaluate this derivative at a particular point, let's take a point x equal to 10 right here, right? The x equal to 10 on this curve would be right here. If I evaluate the derivative at x equal to 10, I get minus 1.6, right? Okay. What this tells us is that the function is increasing in the negative x direction, right? Because you have a minus sign right here, right? You have a minus sign right here. So the function is increasing at x equal to 10. The function is increasing in the negative x direction, right? So if you were sitting at the point x equal to 10 and you wanted to move to a higher value of that function, if you wanted to move to a higher value of that function, what you would do is to x, you would add perhaps a small multiple, a small positive multiple of the gradient, right? Right? So this x is 10, right? And if to 10 you add a small positive multiple of the gradient, this is the gradient at x equal to 10 minus 1.6. And when I say a small multiple, let's say you take, let's say alpha is 0.25, 1/4. So this would be equal to minus 0.4, right? And you would move to the point 9.6, right? So if from x equal to 10, if you were sitting at x equal to 10 right here, and you move to the point x equal to 9.6, you can see that the value of the function would have increased, right? So if you move in the direction of the gradient, you see an increase in the value of the function. Okay. Now I slid a small alpha in here. I called it a small multiple, a small positive multiple, but I need to spend a minute talking about why this is required, right? Now you know that in general, the value of the derivative changes from point to point, right? So the way the function behaves here, it's a nice parabola that you can see in front of you, and perhaps instead of moving to 9.6 you could have moved even further. But in general, you're better off taking a little bit of a conservative approach, and rather than adding a large multiple of the gradient to the point, you're better off adding a small positive multiple, right? So perhaps alpha could be 0.25 like we took in our example, right? So to recap, if I wanted to increase the value of the function from where I am currently sitting, right, I would add a small positive multiple of the gradient evaluated at that point, right? So this let's keep in mind. Let's move further. Multiple variables. For a function of multiple variables, the partial derivative with respect to each variable arranged as a vector is called the gradient, right? Which calculated at a point tells you the direction in which the function is increasing the most. Okay, very important. In one dimension, the example that we saw earlier, there are just two directions, right? Plus direction, minus direction. But once you start going to multiple variables, even two variables, three variables, etc., you have infinite directions, right? Infinite directions. And if you calculate the gradient of a function at a particular point, it tells you the direction in which the function is increasing the most, right? So let me again take an example. These examples are difficult to draw, so I'm going to, on a piece of paper, so I'm going to sort of take an example from real life. I have shown a hiking trail over here, some mountains, some sand dunes, etc. Okay, and let's imagine this situation here, where let's say the east-west direction is the x direction, right? The east-west direction is the x direction, and the north-south is the y, right? I mean, let's assume like a flat earth at this particular point, and let's assume the x and y axis to be, defined by east, west and north, south, right? And the value of the function at each point, at each x and y, is basically the elevation at that particular point. Because as you can see, the elevation, there are sand dunes, there are mountains, etc. So the elevation changes. And imagine that this is a function. Imagine this is some sort of an elevation function which takes different values for different values of x and y, right? Okay. Now suppose you are at a particular value of x and y, right? Suppose you are sitting at a particular value of x and y right here, right? And you had this function. I mean, this looks like a fairly complicated function, but let's say you could calculate its derivative, and you calculated the derivative at this red dot that I have drawn right here, right? I'm talking about the derivative with respect to each of these axes. So the gradient, and let us say the gradient evaluated to, let us say, a vector. It would be a vector, let's say 3 and 2, right? Let's say it evaluated to this vector over here. What it means is that your elevation would increase the fastest if you traveled 3 steps along the x-axis and 2 steps along the y-axis, right? So let's say if you were to travel somewhere in this direction, let us say, the function, the value of the function, which is the elevation over here, is likely to increase the fastest. Okay. So if you were sitting at a point x0, y0, let's say this red dot that you had drawn was point x0, y0, the point, if you wanted to increase your elevation, the point you would need to go to would be some multiple, like I said, alpha times 3, the vector 3, 2, right? So again, x would increase by 3 units, y would increase proportionately by 2 units, and you would move to a point over here. This is the new point right here, whose elevation would be higher than the elevation of this point here. Okay, so that is what the gradient means in multiple dimensions. And if you want to move to a point which has a higher value, a higher function value, elevation in this case, you essentially add a small multiple of the gradient. You add a small multiple of the gradient to that point, to the coordinates of that point, and that gives you the point that you want to move to, right? Exactly similar to what we did in one dimension, but this is the multi-dimensional analogy. Let's move. So we were talking about increasing the function so far. If you wanted to reduce the value of a function, you have to travel in the direction opposite to the gradient. That is the direction of the negative gradient. Okay. So let's keep these basics from calculus in mind. Okay. Error as a metric and error minimization. Okay. One commonly used metric is the error. Okay, error is often used as a metric for optimization, and what you perform in the course of optimization is essentially error minimization. So let's see how error minimization works. The first thing you do is, of course, define the error to be minimized. Again, the error could be defined in multiple ways, but you essentially define the error that you want to be minimize. You find the gradient of the error at the point where you are. Okay, remember we just looked at gradient. You find the gradient of the error at whatever point you are, and finally you take a step in the direction of the negative gradient to move to the new point and thereby reduce the error, right? So the gradient of the error function tells us the direction, the direction of the negative gradient, because you want to minimize, not maximize the error. The direction of the negative gradient tells you how you need to move, where you need to move in order to reduce the error, right? So this is how using error as a metric and error minimization as an optimization technique works. We are going to discuss this in slightly more detail. Okay, the reason I say that error is often used as a metric, especially in problems that have to do with AI or the kind of optimizations that we are going to run into, the reason why I say this is a commonly used metric is as follows. Many times what you're trying to do is essentially build a mathematical model that mimics the behavior of your training data. Okay, so you gathered a bunch of training data, okay, which is training data is essentially a combination of inputs and their corresponding outputs, and what you're trying to do is model this input output behavior using a mathematical model. This is what you're doing most of the times, right, in problems in AI. Now this mathematical model has parameters, right? It has certain variables, it has certain controls, it has certain knobs which you turn around, right? And let's call these parameters W1, W2, W3, etc. Now, in the case of the binary linear classifier that we saw earlier, these parameters of the mathematical model were essentially the coefficients of the feature variables, right? I mean, the coefficients of the hyperplane that we've been talking about. So you have these parameters of the mathematical model, and the behavior of this model is of course a function of these parameters, right? The model behavior changes with changing values of these parameters. I have drawn this capital W as a vector to indicate, all the smaller W's considered together. Okay. Now, as I said, the mathematical model is being constructed to replicate the input-output behavior observed in the training data. Okay. To understand this, let's just consider an example, right? So let us say this was your training data, right? The training, each of the points in your training data is indicated by a column over here. Okay, the rows are the different feature variables. So for example, the training data point 1, the first point in the training data, had various values of the feature variables 5, minus 4.7, 1.1, etc. So this is the feature vector. This is the first feature vector, or the feature vector corresponding to the training data point number 1. This is the feature vector for training data point number 2. This is the feature vector for training data point number 3, and so on and so forth, right? Maybe let's say you have 2000 points, 2000 of these, right? A big training set. Okay. What your training data also has is the recorded output or the observed output when for these feature variable values. So when the values of the feature variables were 5, minus 4.7 and 1.1, the observed output as a part of your training data gathering was 42.2. Similarly, when the values of the feature variables were these, your observed output was, let's say, 69.3, and so on and so forth, right? So this input, this is the input, right? This is the input, this is the output, right? So this input-output behavior is what this mathematical model is supposed to replicate as best as possible, right? Okay. Now suppose your mathematical model, you had constructed a model and you had selected certain values of W1, W2, W3 and so on, right? And you gave it the first training data as an input, right? So you passed 5, minus 4.7 and 1.1 as input to this mathematical model. This mathematical model would give you a certain output, okay? Similarly, for other feature variables, it would give other outputs. Let's indicate them in this table. So let us say when you gave 5, minus 4.7 and 1.1 as an input to this model, the output returned by the model was, let's say, 22, right? So 22, right? Similarly, instead of this, if you gave, let us say, 7, 5, 6.5, which is the second training data, which is the second point in the training data as an input, you would observe the output to be, let's say this model returned 48.9. So that is the way in which this table has been tabulated, right? So the recorded output in the training data, what you observed, and the output returned by the model for certain values of these parameters W, right? What you would ideally like is for these two numbers, these red and green numbers, to be as close as possible, right? And if that happened, you could claim that the model was replicating the behavior of the training data very well. Okay, so you want to select the values of parameters W1, W2, W3 and so on and so forth, so that the difference between these two, the difference between the red and the greens for each training data is minimized, right? You could say that the difference between the green and the reds is actually the error, right? It is the error. This is the error made by the model 42.2 minus 22 is the error made by the model for the first training point, right? Similarly, 69.3 minus 48.9 is the error made by the model for the second training point, and so on. So it becomes convenient, assuming that all training data has the same level of importance, all training points have the same level of importance. It becomes useful to define the error as a summation over all the training points, okay, as a summation over all training points, let's call them k, the running variable, of yk minus zk, right, where yk is what you wanted it to be and zk is what your model returned, right? And if you divided all of these by the total number of points, which was 2000 in your case, you would have the average error per point, right? So you add up all the errors, divide by the total number of points, you get the average error per point, right? There is a small problem in this. Sometimes the error can be positive, sometimes the error can be negative, and you don't want to be in a situation where the final error is really small, although the individual errors were large, but they just ended up cancelling each other, right? To avoid that kind of a scenario, what you could simply do is take error square, right? Take yk minus zk square, right? This is what is known as mean square error. Mean square error. You add up the errors, you add up the differences between the recorded output in the training data and the output returned by your model for every point in the training data. You add it up, you divide it by the size of the training data, right? And you of course take the squares to make sure that, you know, all the errors are positive and they add up. This is the definition of mean square error, okay? And if you use this as a metric, it's a good metric to use, because effectively what you would be doing if you minimize this mean square error is essentially making sure that the recorded outputs and the outputs returned by the model are as close to each other as possible, which is what you want, right? Now I have made a mess on this slide, so I want to clean it up. I want to move to the next slide. Mean square error as an example. Okay, error is going to be defined as computed value, the value that is returned by your model, minus the expected or the recorded value square. This is the square error. This is the square error. Okay, and here yk is the output in response to the input xk, right? In response to the input xk, and it's a function of the specific values of the weights, like we said. Mean square error is you add the square error for all observed points and divide by the number of points. So this is your definition of the mean square error. Don't be intimidated by the formula or the annotation. All it's saying is that for an input point A, this is the output returned by the model. For an input point number k, this is the output returned by the model. This is what was observed in the training data. You take the square, so it's all positive. You add it over all the inputs. This is the summation over k, and divide by the total number of points. M is the total number of points in the training data. Total points in training data. Right? This is your mean square error. You find the gradient of the mean square error. Okay, now again applying chain rule, the gradient would be essentially this, okay, where f dash k of w is the gradient of this function f, okay, is the gradient of the function f. So here this is a scalar, this part is a scalar, this part is a scalar. This scalar multiplies this vector, gradient is a vector. This whole thing is a scalar actually. This multiplies this vector and your gradient is a vector. Okay. the new values of the weights, like we did in the one dimensional example or the two dimensional examples, we moved the point based on the gradient. Your new values of the weights, W new is W old minus, why minus? Because it's an error that we want to minimize. So we want to move in the direction of the negative gradient. Alpha is the step size that I talked about earlier, a small positive number multiplied by this gradient, computed at the particular value where you are, computed at W old. Okay. So let's stare at this for a moment. Let me clean this up. You can stare at this for a moment. W new is simply W old minus alpha times the gradient computed at the older values of W. Okay. So what this is going to do for you is your W new is going to result in a lower mean square error than W old. Okay. This is your mean square error for W new. This is your mean square error for W old. And if you moved from W old to W new using this sort of a gradient based approach, your new mean square error is going to be less than your older mean square error. And you keep doing this. You keep repeating this. Once you move to W new, your W new is going to become W old. You are going to calculate the gradient for that point, move to an even newer point, and so on and so on and so on. Right? Okay. Now, the gradient of the function f enters the picture here, and therefore it's a good idea to select models where, for the gradient descent, where you can find the gradient easily, right? I mean, you need to be able to find the gradient of the function and evaluate it at a particular point in order to be able to move to the new point, right? So your model has to be that sort of a model. Let's take a very specific example of a linear predictor. This is slightly different from the linear classifier that we talked about. But in a linear predictor, the computed value yk is simply W transpose times xk, the vector, the input vector xk. So each value of the each coordinate, I will say, in the feature vector is going to be multiplied by a weight. That is our model of a linear predictor to give the output value y. Okay. And if you sort of go over what we did over here, your mean square error is again the same thing, except that for a linear predictor, your gradient is pretty easy to find. This is your mean square error. Your mean square error is simply W transpose x times xk squared added over all k. And your gradient is simply this because of chain rule, right? I mean, because of chain rule, the derivative of W transpose xk is simply xk. So this part here is a scalar. I mean, I should say this part, right? I should say this part. This part here is a scalar. This part here is a scalar. Xk is a vector. Xk is a vector, and dEw by dW is simply this, right? Is simply this. And what you're going to do, the new values of W for the linear predictor are simply going to be W new equal to W old minus alpha step size into this gradient that we had found, right? Gradient that we found, evaluated at W old, right? So this is how you would optimize a linear predictor. Okay, you often try to sort of visualize this with some drawing, some graphics. I mean, this, for example, let's say that this is the point, this is the point, these are the values of W where your error gets minimized, and you're starting off over here, and at each step of the iteration, you sort of take a small step. You take a small step and sort of move towards the final. I mean, the direction, the gradient direction you're going to get is not going to directly point to the final minimal point, but you're sort of going to sort of maybe go a little bit here and there, and then finally converge, right? These are your iterations. When do we terminate? When do we terminate? When do we terminate the iterations? We terminate the iterations when the error reduction is minimal, right? So in every iteration, your error is reducing, and when the error reduction ends up becoming negligible in subsequent iterations, that's when you terminate. I mean, this is very similar to, you know, you would have seen these people making sugarcane juice in their machines on the roadside, and they keep passing the same, iterating the same sugarcane again and again in their machine, in their crusher, and they finally stop when, you know, the amount of juice they are getting is not justified by the efforts they have to sort of iterate with that sugarcane. So when the amount of sugarcane juice that you get per iteration is very, very little, that's when you sort of throw that thing away, right? So that is exactly the philosophy that is used in terminating the iterations in these error minimization type of optimizations, right? Okay. So where are we? Okay, let's take a quick let's take a quick look back on where we are, right? So we said at the beginning of this lecture, when we talked about choosing a metric, that the metric should first of all reflect what you want to accomplish, right? And minimizing the error, minimizing the average, the mean square error, minimizing the mean square error seems like a reasonable metric to choose from a point of view of what you want to do. Assuming that all the training data points have equal importance, you want to sort of minimize the average error averaged over all the points in your training data. So mean square error sort of satisfies that requirement, reflects what you want to accomplish. At each iteration, we should know how to modify the weights to improve the metric. This is where our gradient came in. This is where our calculus came in. And if you selected a model where this gradient could be found and evaluated at each point, it would tell you how to modify the weights in order to improve the value of the metric at every iteration, right? So point number 2 is satisfied. We should know when to terminate. We talked about that with the sugarcane example. When the incremental benefit sort of becomes trivial, becomes very, very marginal, that's when you want to terminate. Termination should be at a global minimum. So under by and large, it's been shown, and that's sort of not a part of this particular lecture, that if you use criteria like mean square error, and if you use sort of gradient approaches to optimize or minimize the mean square error, the minimum that you end up is indeed the global minimum under, you know, fairly common constraints. So this you will have to assume at the moment. Computationally efficient. This is a problem that we have not addressed, and this is what we are going to address now. So the first four criteria have been nicely addressed by the error we took with our gradient based approach, gradient descent approach as we called it. And now let us focus our attention on computational efficiency. Right? Okay, we are going to discuss gradient descent types. Okay, now remember, this was our mean square error. And to calculate the mean square error, we essentially summed up over k over all the training data the square error for each individual point in the training data. Now if let's say we said m was 2000, right? So you have to sort of calculate the square error for 2000 points, add it up together to get the mean square error. Okay, and then you proceed to minimize it, right? So this is fairly computationally intensive, I mean, for every iteration, and then you end up sort of taking small steps all the way to the optimum. Each step is going to involve these calculation over 2000 points. So that's pretty computationally intensive, right? Stochastic gradient descent. Okay, stochastic gradient descent is a clever idea, okay, which says that instead of using all data points from the training set in each iteration, use one random point from training set for each iteration. Okay, let me repeat. Here, what you are doing in your traditional gradient descent is computing the mean square error over all points. You are averaging it over all points in the training data, right? All the data points, right? What stochastic gradient descent is saying is use one random point, one different random point from the training set for each iteration. So this summation basically goes away entirely. Okay. So what you're doing 2000 times in every iteration, you just do it once by selecting a random point. Now, this is a particular, it almost seems like an outrageous idea, right? How can we just take one random point and decide our direction based on that? Okay. The word stochastic, what's the meaning of the word stochastic? I mean, if hopefully at some point in time, I'll do a lecture series on signal processing and we will talk about what stochastic processes are over there. But for the moment, think that the word stochastic basically means probabilistic. Okay, probabilistic. And sort of in a hand waving fashion, what I'm saying here is that the philosophy behind stochastic gradient says that if your mean square error averaged over all your points in a particular direction, then if you were to sort of use a few random points in each iteration over the course of those iterations, you would probably be going in the similar direction. Okay. That's sort of the idea behind stochastic gradient. But what the stochastic gradient descent algorithm does is this summation that was here and averaging has gone away completely, and your new weights are simply old weights minus this gradient. I mean, there was just 1 point, so this is the gradient, right? Okay. So you suddenly simplified this by a factor of 2000, or whatever training data set you had, right? So this is of course computationally much more efficient. However, because you are not averaging, what averaging does is that it protects you from some wild swings. In the stochastic gradient, what is probably going to happen is from one iteration to the next, your directions are going to be pretty random. Okay. Sorry. And you could probably imagine that you would need a lot more iterations to end up at your final answer if you're doing stochastic gradient, because you were choosing a random point and random points would point you in random directions. But the theory is that over the course of using many of these, the eventual direction that you end up with is going to take you to the global optimum in any case. Okay, so although the number of iterations in stochastic gradient are likely to be more, the computation that you have to do per iteration is substantially less. Batch gradient descent. So if you are not a completely adventurous type of a person, and if you think that stochastic gradient is sort of a little too outrageous for you, you could do something a little bit more conservative, neither here nor there type of a thing. Batch gradient descent, where you average over p points, okay, not over the entire set. So you choose p. P is substantially less than m for typically. So if your m was 2000, you would maybe pick p as 20. I don't know, some small number. Not 1. If you were doing 1, that would be stochastic gradient, and you average the mean square error. You compute the mean over only p points. So instead of doing 2000 computations in every iteration, you're doing 20. You're being a little bit more conservative, but you are probably not going to swing as dramatically as you were swinging in the stochastic gradient descent from one iteration to another. So batch gradient, instead of using all data points from the training set in each iteration, use few points from the training set for each iteration. Okay, and you still have this summation over here that you had in gradient descent, but it is over only p points, where p is much less than m, which is the total size of your training set. So this is batch gradient descent. Okay, so like I said, your stochastic gradient was highly random. Let us say your this was your basic gradient search where you had averaged over all the 2000. It was, you know, fairly sort of, the direction changed, but it did not change dramatically. Perhaps your batch gradient is not going to be as steady as gradient descent. It's not going to be as random as stochastic descent. Maybe it's going to be a little bit more, I don't know, so on and so forth, right? So the batch gradient descent is somewhat of, a compromise between extreme computation on one hand and extreme randomness on the other. Okay. Okay. Use some or all of the training points to compute the gradient, which is the direction, in which to modify each weight to reduce the error. Okay. Modify the weights in small step sizes and iterate till incremental improvement is negligible. Okay. So this was the summary of gradient descent. Again, we said that we would configure the optimization problem by defining a metric and either maximizing or minimizing that metric in iterations till we ended up with our final answer, right? So for gradient descent algorithms, we defined the error as the metric to minimize. In particular, we looked at the mean square error, okay? And what we said was that we were going to compute the mean square error over the training points using either all or some of them. Okay. Compute the gradient of the error function at each point and use that gradient to move the each weight, change the values of the weight in a manner that reduced the error. Okay. And we said we would go in small step sizes for a reason, and we would iterate till the incremental improvement was negligible, right? So this is the summary of gradient descent algorithms. Okay. Again, we discussed gradient descent in the context of mean square error, and we saw how we could iterate to successively minimize the mean square error until we ended up with a good answer. Okay. So that's all for today, and I will see you next time.